Okay, so are there any questions from last days? If not, let's continue with that. So, so last day we introduced the notion of oops, positive roots, right? We defined what positive root is. That is, we had to forcibly choose a basis for our Karta sub algebra. That is some ordering of the basis. And then we essentially defined that the first non-zero root component being positive means it's a positive root. So that way you could define positivity. You could define when two roots were big, one was bigger than the other. Of course, the artificial thing here is that you are fully free to choose a different basis. And even if you chose the same basis, you're fully free to choose a different order. So what looks like a positive root in one choice of basis will not be a positive root in another choice of basis. So this is strictly a basis dependent choice. In that sense, not perfectly natural. However, this is okay. And then we went on to define simple roots, which are positive roots which cannot be as a sum of two other positive roots. The simple root, okay, let's drop the plurals here. A simple root is a positive root which cannot be written as a sum of two other positive roots. Okay. And then we went on to prove a few properties. For example, we proved that the simple roots make an make an obtuse angle between them, or 90 degrees or obtuse angle. So we have already proven before that the only possible angle between roots are 0 degrees, 30 degrees, 45, 60, 90, 120, 135, and 150. If these are for all roots, for for simple roots, these are sorry, I struck off the wrong thing. These are the possibilities. Okay, and we also talked about Dinkin diagrams where you show simple roots by open circles and use lines joining them. And the lines essentially tell you what is the angle between the roots. So you have one single line. If you have no lines, it's 90 degrees. If you have one line, it's 120, two lines, 135, three lines, 150. Okay. We also prove that the simple roots are not only linearly independent, they are a complete set in your space of root vectors. And then we went on to claim that you can actually create, if you know the simple roots of a particular simple Lie algebra, you know all the roots, the full root system can be figured out. Not only that, the complete algebra can be figured out just from the knowledge of the root vectors, which is a huge thing to say. Okay, so today what so I guess this was all covered last time, right? Could you just remind me whether I've covered all of this?
Yes.
Okay. Anything more? I don't remember. What was done last time?
You gave another property that all the any positive root can be written as a non-negative integer
Yeah.
and integer
Okay.
combination, and give an explicit example for SU3 with the phi ones and then the phi twos.
Okay.
Uh,
Okay, that's good. So we will just continue with that. But let me just briefly recap that a bit. What we said was basically, first of all, any root, any positive root, must be of the form phi k, where phi k is k alpha alpha, where alpha here stands only for the simple roots. So there is a sum over only the simple roots. And k alphas are non-negative integers, could be 0, but could be only positive integers otherwise. And k is just a label which talks about the sum of all the k alphas. So you add up all these integers, what you get is the label k. This essentially gives us a way of systematically going from one level of roots to the next. Okay. Of course, we are not claiming that all positive integer or all non-negative integer combinations of simple roots are roots. That of course can't be, because obviously there are infinitely many of these, whereas there are only finitely many roots. So what we need to look at is a systematic way of figuring out which ones are roots, which ones are not. And I've already illustrated that last day using SU3, but let me just quickly repeat what we were doing there. In SU3, we had two simple roots. After all, if you remember your root diagram, these were the six roots that you had in SU3. Remember, SU3 has 8 generators. 2 of them form the Kata subalgebra. There are 6 other generators, and you can diagonalize these 6 other generators in the adjoint representation and get the root vector. So 6 root vectors, and these vectors are this, 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 and this. And because this, we are going to claim, we are going to order the basis in which this is component 1, this is component 2. That automatically tells us that these 3 are positive roots, these 3 are negative roots. This one was sort of easy to understand. And among the positive roots, you can easily see that you can not find a way of finding or writing this as a sum of 2 other positive roots, or this. So these are the simple roots. Whereas this one isn't. So this one is a positive root which is not a simple root. So this is positive, definitely, but not simple. The other, because you can write this obviously as a sum of these two, this one and this one. So what we were claiming is, suppose I just knew these two vectors alpha and beta, and that these were the simple roots, and knew nothing else about the algebra. Okay, we just knew that this is a semi-simple Lie algebra. That much we know. In fact, a simple Lie algebra, and it has these two simple roots, alpha and beta, which are of course given by. So this component is half root 3 by 2, and the other beta is half minus root 3 by 2. Now let's just pretend for the time being that we don't know the entire root structure of SU3. We don't know all the 6 roots. We just know that these are the two simple roots. And how do we go about figuring out all the roots from there? Of course, you just figure out the positive roots, that's enough, because as you know, all roots occur in alpha minus alpha pairs. And if alpha is positive, minus alpha is obviously negative. From the definition, of course, obvious means the way we defined the order. And because of that, you don't really have to look at positive and negative roots, all of them, just positive roots will do. So how do we go about this? First of all, we said we look at phi k, where k is a positive integer, a natural number. So phi 1, for example, is the set of all combinations of alpha and beta. In this case, just alpha and beta, because we have only 2 simple roots. Of course, Lie algebras can have more than 2 simple roots, but for the time being, because we are in a 2-dimensional system, we have only 2 simple roots. Well, phi 1 can be either alpha, both phi alpha and beta are phi 1. So these are possibilities. Okay, and they are both obviously roots because they are just the simple roots. Phi 2, well, 2 alpha, 2 beta, alpha plus beta. These are the possibilities. They are not all roots. And which ones are not is something you can easily figure out, simply because you already know that a multiple of a root cannot be a root. So 2 alpha and 2 beta are out. Only alpha plus beta can be a root. Here, remember this diagram that we have on this side, we are pretending that we don't know anything about it. So we don't know at this stage whether alpha plus beta really is a root or not. Just continuing along this, suppose I imagine that there could have been phi 3s. So what are phi 3s? Possibility 3 alpha, 2 alpha plus beta, alpha plus 2 beta, 3 beta, and so on. Of course, out of these two are immediately out. But the question remains, first of all, is this alpha plus beta at all a root? And if not, of course, then you have, if alpha plus beta were not a root, then the thing would stop there because phi 2 is done. There is nothing in phi 2 then. There would have been nothing in phi 2 then. And then you simply can't have a phi 2. Okay, is that obvious to everybody that if you don't have a phi 2, you can't have anything in phi 3? In other words, if it had so happened, of course, that's not the case for SU3, as you already know. But if it had so happened that all these are not qualified to be roots, so alpha plus beta is also not a root, neither is phi 2, neither is 2 alpha, neither is 2 beta, then you cannot have 2 alpha plus beta as a root. Is that obvious?
Is that because every root in phi 3 should be some root in phi 2 with some translation by phi 1? So if there is no phi 2, is that...
But why do you know that? That's true. That is actually the reason. But how are you so sure that that has to be the case?
I mean, phi 3 has 3 is a linear combination of 3 roots and phi 2 is a linear combination of 2 roots. So.
Well, phi 3 is just 2 alpha plus beta is phi 3, is an element of, is one possibility in phi 3. Of course, there are multiple possibilities in phi 3. 2 alpha plus beta is just a possibility. All I'm saying is, how are you so sure that if 2 alpha plus beta is a root, then there has to be a phi 2?
Because we'll have to, like, there should be a provision for translations, like by alpha or beta.
Yeah, but if you translate, then what happens? Maybe 2 alpha plus beta gets killed. Let's say 2 alpha plus beta. Let's say alpha plus beta did not exist. And this is a situation we will meet later, not here, but in some other algebra, we may have a situation where a particular level, this particular vector doesn't exist. And 2 alpha plus beta is not a root, of course. It doesn't, of course, you can't say it doesn't exist. But 2 alpha plus beta, when you translate it down by E minus alpha, you will definitely get either a root alpha plus beta, or you will get what?
0 if alpha plus beta is not a root.
Yeah, but then what's wrong with having what's wrong with the possibility that E2 alpha plus beta exists? That is, there is an operator like E2 alpha plus beta. Remember, right now we don't know this is a SU3. All we know is this, or we don't know the full structure. We just know that these are the simple roots. Okay, and you're claiming this, that this will of course be up to a constant, nothing but E alpha plus beta. If E alpha plus beta is not there, that is alpha plus beta is not a root, then this has to be 0. I agree. But why is that a problem? Why can't you have E2 alpha plus beta which simply commutes with E minus alpha and E minus beta? So
then E2 alpha plus beta will commute with all the generators.
All the other generators, you mean? Right.
Yes.
And that would mean that you will end up with a non-semi-simple Lie algebra. You have an abelian subalgebra sitting right there, spanned by E2 alpha plus beta. Okay. So this will go against our assumption. That is, so the theory for non-semi-simple Lie algebras is a lot more complicated simply because of this possibility. Not simply because of this, but this is one of the possibilities which complicates the theory of non-semi-simple Lie algebras. That you may have roots at some higher level which you did not have at a lower level. Okay. For semi-simple Lie algebras, this possibility is not there. So that is what makes life very easy for us. Okay. So you're right. So the point is This shift below is not was not impossible, except that if you can't have that and have a semi-simple Lie algebra at the same time. Since we are focusing on only semi-simple Lie algebras, things will be okay for us. Is that clear to everybody? Okay, so the build-up rule is straightforward. You just look at phi 1, which is just the simple roots. Then you look at phi 2, check for which ones are possible, which ones obviously cannot be roots, you just discount them. Then you go for phi 3, and so on. Of course, if at any given level you run out of roots completely, that means you stop there. You can't go any further. So in this case, the check really would be something like this. We want to check whether alpha plus beta is a possibility. That simply means, can I shift up this E beta? Can I shift it up by acting with add E plus? And now maybe I will just put an alpha label here. Remember, every pair, alpha minus alpha, beta minus beta, will have their own SU2 subalgebra, right? Because we are going to talk of several SU2 subalgebras in the long run, we are trying to sort of label which SU2 subalgebra we are talking about. So this, of course, means this. And what we are going to try to ask is are we at all going to be able to raise E beta? Or remember, these are SU2, these generate the SU2 subalgebra, right? These are representatives of SU2 subalgebra. So whatever E beta does on this, or whatever they do to E beta, will depend on which SU2 representation E beta belongs to. Okay. So how do you figure that out? You just look at the E3 value. That is, add E3 acting on E beta, how much is that? Well, we know what add E3 acting on E beta is. E3, remember, is simply alpha. Okay, I'm again talking of E3 for the alpha minus alpha pair by mod alpha square. So the E3 eigenvalue for E beta is simply alpha dot beta by mod alpha square. Okay, and we had already proven earlier that this famous equation that we have is minus half p minus q, which tells you how many times you can raise beta in the direction of alpha. That's p. And how many times can you lower in the direction? That's q. So you just look for that. So in this particular case, this quantity, alpha dot beta by mod alpha square, is straightforward. It's minus half, right? Cosine of 120 degrees. Two unit vectors placed separated by an angle of 120 degrees. So you get minus half. Okay. So what I know for sure is p minus q is 1. But how does it help me figure out what p is going to be and what q is going to be? Can you tell me? I've got p minus q. I've got p minus q is 1. How do I know what p and q are? Can we figure out what p and q are from here?
If we use the add E plus alpha E beta and show that becomes 0, then it's the highest weight
It's
scale.
true, but we don't know that, right? We don't know the algebra yet. All we know are the simple roots. Remember, our premise is we don't know anything about the SU3 subalgebra. If I knew that, I could use whatever you are saying. Okay? All I know is that in a semi-simple Lie algebra, you have roots. Root pairs form SU2s. That theory we know. And here we know that, so E beta essentially will act like an SU2 representation, or a member of an SU2 representation, to be more precise, not a full SU2 representation, but one element of an SU2 representation. Only the three SU2 operators generated by the alpha minus alpha pair, E plus, E minus, E3, will act and produce whatever stuff they do for SU2. And that's very simple, granted. But if I don't know what those operators are at this stage, right? I don't know what the algebra is, so I don't know what exactly the commutators are going to be. My claim is you don't need to. From P minus Q equal to 1, you should be able to tell me exactly how much P and Q are going to be. That sounds like a tall order, because from the difference of two non-negative integers, can you say what the integers are? Yes, can you? Come on, this is a class 3 level question. If I told you the difference of two integers, can you figure out the integers?
No, sir.
Of course not. However, when can you figure out the integers? From the difference? That's a trick question. Trick question meaning the answer is so simple that it may be eluding you. Given the difference of two integers, when can you figure out the two integers?
You
Come
need
on.
one constraint.
When? What?
One
What?
more. You need one more
Yeah.
condition.
You need one more thing, right? One more information. One more piece of information from wherever. Just from the difference, you cannot find out the values. However, let me first point out that even if you did not know the values here, you would know one thing definitely. What do you know about P and Q here? You know that P and Q are non-negative integers, right? Okay. So that tells me that P has to be at least 1 or more. Is that clear? Yes or no?
Yes, sir.
Yes.
That means you should be definitely able to raise beta in the direction of alpha at least once. So if your only question was, is alpha plus beta a root? The answer is yes. Right? Clear? Is this okay?
Yes.
Now, I will point out that actually you know more than that. Because in this case, you know what Q is. Can anybody tell me how do you know what Q is? Q, remember, is how many times can you shift beta in the direction opposite to alpha?
Should be 0 because both alpha and beta are simple.
And hence,
Q should be 0.
why?
If Q is 1, then assuming Q is 1, then we can shift beta in the direction of alpha, lower the beta
Good.
of
Good
alpha
then.
once. So
Right.
beta will be written as beta minus alpha plus alpha, so beta won't be simple.
Okay. Almost correct, except that that's not an impossibility. Why? For beta,
Beta minus alpha can be negative.
beta minus alpha can be negative, right? However, if your argument is right, the point is we had already proven in the last class that if alpha and beta are simple roots, then alpha minus beta cannot be a root. Why? Because you have given me only half the answer. If this is not a contradiction, if beta minus alpha is negative, right? If beta minus alpha were positive, then this is a contradiction. You can't have a simple root as a sum of two positive roots, right? But if beta
Then
minus
it is
alpha is
the other
negative,
one.
then alpha minus beta is positive, and then you are writing alpha as alpha minus beta plus beta, which is a contradiction. So either this is a contradiction or this is a contradiction. One of them is a contradiction. I can't be sure which one, but one of them has to be. Is it okay? So the rest of your argument is fine. Because of this, we know that beta minus alpha cannot be a root, which means you cannot shift down, which means Q has to be 0. And that means here P has to be 1. Okay? Clear? Which means alpha plus beta is a root, but 2 alpha plus beta cannot be. You can shift beta once in the direction of alpha, but not more than once because P is 1. Clear?
Yes, sir.
What about alpha plus 2 beta?
Now we can use the opposite argument that
Yeah,
beta dot.
you could of course use this beta dot alpha by beta square. That's P minus Q for the beta shift. And that also works out to be the same exactly. It's minus 1. That's Q minus P, of course. So P minus Q is again 1 for that. And again Q is 0 for that for the same reason. So P has to be 1 for that. So once again, alpha plus beta is where you stop. You can't go to either this or this. Okay? So this is critical. This is a very important part of the argument. But let me just point out that even if you had not spotted that, what you could have simply asked is something like this. Say I've got alpha plus beta, and I'm asking, is alpha plus 2 beta possible? All I have to do is I would just take a look at this quantity. Can I shift alpha plus beta again? And how much is this? Well, that's of course 2 from the first beta dot beta thing, minus 1, so that's 1. So Q minus P is 1 here. So why does it tell me that P, for this particular situation, trying to shift alpha plus beta in the direction of beta, I've got Q minus P is 1. But how do I know that this will tell me P is 0? That I can't shift any further? Remember, this Q and P are for the alpha plus beta root, not for the original one. I'm asking, can I shift alpha plus beta in the direction of beta? Of course, I can't. I already know that because we have already figured out that, well, you can't shift alpha in the direction of beta twice. We have already figured out that for that, P was 1. But let's just say we missed that. And there's a reason why I'm saying this, simply because in later situations, this argument will also be useful. So let's just say I've missed the fact that I can't shift alpha in the direction of beta twice. I already know that alpha plus beta is a root. I'm now asking from there, starting from this, can I shift it in the direction of beta? So I end up with this quantity. Right? And this will tell me that Q minus P is 1. And my claim is this is enough to tell you that P is 0. And this is a critical thing in the rest of the construction. Very, very simple thing. How do I know that this has to give me P equals 0? That's sort of obvious, but let's see whether you can see the obvious part of it.
If we shift it by once, we'll get alpha. We'll shift it down by once.
Yeah.
We'll get alpha.
The question is, can you shift alpha plus beta? You're right. In the direction of course, yes. You get alpha equals 1 there. That's how you end up at the simple roots, right? And you can't shift it more than once because you know that a simple root cannot be shifted down by another simple root. Clear? So we know that here Q is 1. I can shift it down once. I hit alpha, which is a perfectly genuine root. And if you go in the other direction, that will tell you that P has to be 0. Sorry, Q is 1, P is 0. Is that clear to everybody? The point I'm trying to make is the history by which you have arrived at a particular root at a particular level actually already tells you what the Q value for that particular root is. You can just have to see whether how many times can I shift down. And so you can find Q from there. So Q minus P will also give you P. How many times can you go up? Now, this may seem like a bit of a trivial waste of time because, after all, here we already have found out the 3 positive roots, which are alpha, beta, and alpha plus beta. Done. So 3 positive roots, 3 negative roots. They're negatives. And I'm done. These are all possibilities, right? Because, by the way, I did not know that SU3 started, or at least I'm pretending that I did not know that SU3 has 6 roots. All I'm saying is, well, I found out that there are 3 roots and that's it. Because 3 positive roots and that's it. At 3 level, all the candidates fail. So I can't have a 4, 5, and 6, and so on. 1, 2 things end there. So my entire root system has been reconstructed. Is this clear to everybody? Yes? No? I want a response.
Yes, sir.
Okay. Now, the next claim was, not only do I end here, of course, I know that there are 8 generators of SU3 now, even if I did not know that, even if I had not known that before. Why? Because each of these 6 roots correspond to a generator. And because I have 2 simple roots, my root space is 2-dimensional. That means there are 2 Karta generators. So, in the end, 8. Okay. I am claiming that I can actually find out the algebra of these roots from here.
Sir, could you repeat the flow, what you just said?
Okay, the argument was 3 positive roots, the 3 negative counterparts, 6 roots. So 6 generators corresponding to the 6 roots. Okay. But we started with 2 simple roots. Now, why 2 simple roots? But we have already proven that the roots are complete in this root space. That really means the simple roots are complete in the root space. That means 2 simple roots can span the entire root space. So my root space has to be 2-dimensional. Okay? And 2-dimensional root space means what? Means the root vectors, which are just eigenvalues, which essentially label the eigenvalues of the Karta generators, there are 2 eigenvalues for each. Right? It's a 2-dimensional scenario. That means there are 2 Karta generators. Of course, we usually approach this, the way we came to this was the other way around. We started with the saying, okay, let's start with a fact that you have a Lie algebra, then you have a Karta subalgebra, which is a maximal set of commuting operators, commuting generators, and so on. And then from there we came to this. Here I'm just showing you that if you just know the simple roots, you can reconstruct that part of the thing. At least how many generators is there, and what are all the root vectors, and so on. My next claim is, from what we know and from the properties of simple roots, we can actually reconstruct the entire algebra. We can figure out what the commutators between these generators are going to be. Okay, so that is the claim really is all these commutators. Now we have 2 Karta generators and we have so these 8 generators, we should be able to now write down the commutation relations between them. Notice that this is a huge claim. The commutation relation system, when you start with SU3, if you just write down the 8 traceless 3x3 matrices and then try to find out the commutators, you get a rather complicated set of relations and so on. And then it takes a lot of work to get here. What I'm claiming is if somebody told you that the simple roots are these, then you can not only find out what all the roots are, you can find out the entire algebra. There's all these commutation relations, etc., can be figured out. That's a claim. I've not shown you how to do it yet. I'm just claiming that. Okay. And I'm going to substantiate that, but I think I will not do it today. I will leave something for the last day. Or not the last day. We have 3 more classes, hopefully. So we'll have time for that. But today what I want to do is, okay, I will try coming back to SU2, SU3 and its algebra if I have time after I finish the next example. The next example, again, stolen from Georgi, is a group called G2. I want to show you how to construct the root structure. As I said, SU3 unfortunately is too simple. As a result, what happens is, if you're dealing with SU3 and only SU3, you don't get to appreciate the full power or all the subtleties of the thing that you get to do here. So let's look at a slightly more complicated example. Again, a simple rank 2 Lie algebra, something which has 2 Karta generators, so root space is 2-dimensional. And the possible and the simple roots here are simply these. So this is one simple root, 0, 1. Just hold on. Okay, sorry about that. Let's come back. So, as I said, 2 roots, and one is a unit vector, the other one is not, the other one is longer, and of course it points somewhere here. It would have actually been somewhere further down. Okay. So, first of all, you should check whether this is at all possible. If somebody claims that these are simple roots, can they be simple roots? The rule for that you have to remember is, well, you know that only certain angles are possible. So you can see whether this fits. So alpha dot beta is of course minus 3/2. So the great thing about this is once you've got the theorems out of the way, the rest of the calculation is simple class 12 stuff. So twice alpha dot beta by alpha mod square. That's of course minus 3. And twice, okay, I should really write beta dot alpha, although it's, as you all know, it doesn't matter. The order doesn't matter, but this way you are, if I write it this way, it's easier to figure out that I'm talking about raising E alpha in the direction of beta, and this is raising E beta in the direction of alpha. So these 2 equations, what do they tell us? Yes?
A number of ways alpha can be shifted. Uh,
and beta can be shifted. In fact,
beta.
the first one tells you how many times can you shift beta in the direction of alpha, which is 3 times. Remember, this is twice, this is minus p. This is actually minus p minus q, but you know that for the simple roots, q has to be 0. Beta cannot be shifted down. So p has to be whatever is the value you can see. So this says for E plus alpha acting on beta, p equals 3. For E plus beta, that is the AC2 algebra generated by beta and minus beta, acting on alpha. Okay, I will either put the arrow or not put the arrow depending on my whim, but you know that I'm referring to the same thing. P is 1. So what that tells me is that if you just think of things at this level, alpha plus beta is a root, 2 alpha plus beta is a root, 3 alpha plus beta is a root, right? Those are the 3 roots I get when I shift beta in the direction of alpha up to 3 times. Of course, the other one, E plus beta acting on alpha, tells me that beta plus alpha is a root. But that's not a surprise, that we have already found out. There's this one, the same as this one, so no point in counting it again. It also tells me things like 2 beta plus alpha is not a root. You can't shift alpha in the direction of beta twice. Or 3 beta plus alpha is not a root, and so on. Okay? So we already know some of the possibilities. So we have already seen that we started with 2 simple roots. We have already got 3 more. But the question is, do we end here? The answer for that is, now we have to be a lot more systematic. Okay, I put this somewhere. So what we have, remember, this is a critical point, alpha dot beta by alpha mod square is minus 3 twice beta dot alpha by beta mod square is minus 1. These are going to be the defining important relations that we have. By the way, the length, this also tells you that alpha square beta square length ratio has to be 3, which is fine. That's part of the restrictions we had. And maybe I should have also mentioned that this actually tells you that the angle between alpha and beta has a cosine of minus root 3 by 2, which is something you can easily figure from here, which means the angle between alpha and beta is actually 150 degrees. And the Dynkin diagram corresponding to this would be 2 simple roots, 3 lines. 3 lines because of the 150-degree angle. So now, let us recap what we have found out so far. We have found out the phi 1 level. Of course, you have alpha and beta. Phi 2 level, 2 alpha, 2 beta is out, so we are not going to write them down. Alpha plus beta. Phi 3 level. Phi 3 level had 3 alpha, 3 beta, not a possibility at all. 2 alpha plus beta. And alpha plus 2 beta were possibilities, but alpha plus 2 beta is not, as we have figured out. So at phi 3 level, only this. At phi 4 level, we have 3 alpha plus beta. But okay, let me just write down all the possibilities first. What were the possibilities? 4 alpha were a possibility. We know it cannot be a root. 3 alpha plus beta. Then 2 alpha plus 2 beta. Then I can easily eliminate all of these. These are multiples of roots, so can't be roots. Right? Because alpha plus beta is a root, 2 alpha plus 2 beta cannot be. And this is not a root because you cannot shift alpha in the direction of beta more than once. So even at phi 4 level, we have only this. Okay. But what about phi 5? Can we go further? Are you with me so far? Any confusions? None, hopefully. So 5, 5. I'm not even bothering to write down 5 alpha. Okay, let's write them all down anyway. Doesn't matter. 5, 5, 5 alpha. 4 alpha plus beta. Then 2 alpha plus 3 beta. Then alpha plus 4 beta, then 5 beta. Now, out of these, a few you can immediately eliminate. So, which ones are those?
5 alpha, 5 beta.
Okay, 5 alpha, 5 beta are obviously out. More. You can eliminate more of them.
4 alpha plus beta.
How can you eliminate that?
We
Argument.
because we can only shift beta along alpha 3 times, not 4.
Good. Done. Any more you can eliminate?
2 alpha plus 3 beta.
Why?
Because we only have 3 alpha plus beta.
Right.
Shifting beta twice and shifting beta once, shifting alpha once works now. So this will stay.
I'm not sure it will stay, but the point is, can you immediately eliminate it with a simple argument? You have 3 alpha. So, which one are you trying to eliminate?
2 alpha plus 3 beta.
Okay,
But
that's an easier one. Let's eliminate the easier ones first. There's one more which you can immediately say is cannot be a root. This one.
alpha, yeah.
Because you cannot shift. Can't even shift alpha in the direction of beta once, more than once. So 4 beta is definitely out. So there are two possible candidates: 3 alpha plus 2 beta, 2 alpha plus 3 beta. Okay. Now you can immediately rule out one of them again, which is you were giving an argument. So try the argument again. One of them can be ruled out almost immediately. How can you get 2 alpha plus 3 beta by shifting by a simple root? You can get it by shifting by alpha from alpha plus 3 beta, which can't happen because the alpha plus 3 beta is not a root, right? Or you can start shift by beta. Which one? 2 alpha plus 2 beta, which is also not a root. So this one is again out. Clear?
Yes.
So you were right. 2 alpha plus 3 beta is not possible. But why is it not possible? Because for it to be obtained by shifting from something by a simple root from a previous level, you would need to have those roots in the previous level, which you don't.
Yes.
3 alpha plus 2 beta is still a possibility. Okay. Notice that we proved that you cannot shift alpha in the direction of beta twice. But we have no proof that 3 alpha cannot be shifted in the direction of beta twice. In fact, 3 alpha was not even a root. So you didn't even have that information, or you had no way of accessing that information. Okay. The question really that you have now is, can 3 alpha plus beta at all be shifted? Notice that's an entirely different question. That's something you cannot answer on the basis of whatever we have seen so far. Is this clear to everybody? There's something you have to figure out again. So 3 alpha plus beta, the question is, can I shift it in the direction of beta? The answer is here. You have to ask what is the E3 value for 3 alpha plus beta for the SU2 subalgebra spanned by beta and minus beta. That's always what is going to tell you, can you move up or down? And instead of the E3 value, we are looking at the twice the E3 value because we know that's Q minus P. Okay. So how much is this? Anybody tell me quickly how much this is going to be? That's sort of trivial. The next second term of V3 plus 2. What do you have in front of that? Come on.
Sir, could you repeat the question?
No, I'm just asking for the value of this. The simple dot product. You don't have to calculate again. You have all the ingredients. Of course, that was in the top of the page, but all the ingredients you need are here. You just need these two. Twice beta dot beta by beta mod square is of course 2. And how much is this?
-9.
No, it's -3. You were talking of this one, right? But that's not the one. This is the one. Remember, these two vectors are not equal in length. So alpha mod square and beta mod square are different. Beta mod is √3 times as large. Got it? Yes? No?
Yes, sir.
Maybe? So this is -1. So this is Q minus P of -1. Okay. But now from this, to figure out how much P is, you need to know how much Q is. Or you might even say that, okay, I don't even need to know more, because at least because Q is non-negative, if this is going to come out to be -1, P has to be at least 1 or more, right? So I should be able to shift and get 3 alpha plus 2 beta as a root. Is it okay? If Q minus P is
Yes.
-1, then P has to be at least 1, right? Because Q cannot be less than 0. But frankly, you don't need to argue like that. You can easily find out what Q is. How much is Q for this? Simple question. Ask yourselves, how many times can you shift 3 alpha plus beta in the direction of minus
0.
beta? You can't, right? Because if you shifted, you would have ended up with 3 alpha, which you know can't be root. So you can't shift 3 alpha plus beta in the direction of minus beta. So that has to be, Q has to be 0. So Q is 0, P is 1. So 3 alpha plus 2 beta. Okay, I'm somehow getting the thing stuck somewhere in the middle. Okay, let me just at the end. So, sorry. So 5, 6, 5, 5, 3 alpha plus 2 beta is possible. It is a root. Okay. So can we go any further? So among 5, 5, there's only one, 3 alpha plus 2 beta. Notice that this is what is important to realize is just because you know that you can shift beta 3 times along alpha and alpha once along beta, that information is not enough, because that information wouldn't have told you that this is also a root. You have to go step by step. That information told you this is a root, this is a root, this is a root. Okay. And we also figured out that none of the other possibilities along phi 2, phi 3, phi 4 are roots. Or rather, obviously. But phi 5 has one possibility which does not follow in this pattern at all, but you can find it out by shifting by beta, 3 alpha plus beta. Okay. Of course, you can't shift by alpha for alpha to get here. You could say, why can't I shift by alpha? The answer is because you already know that the maximum number of times you can shift beta in the direction of alpha is 3 times. So that rules out this one. Of course, if you had forgotten about that, you could still check. Ask this question, how much is this? And how much would this come out to be? This would come out to be 6 and minus. But now you have to use the fact that 3 alpha plus beta has a Q value of 3, because I can shift it down 3 times along alpha, along minus alpha actually, and get to still have a root, right? So Q is 3, so P is 0. Of course, you don't need this information, but sometimes in a more complicated situation, this kind of information would help. Okay, what next? Do I stop here? So I don't mean do I stop the class here. I mean do I stop the process here?
We should try 5, 6.
Of course, you should try 5, 6. You will stop only when at a particular level there is no other possibility. All of them are ruled out. So 5, 6, I don't even look at all the possibilities. Just look at these two. This is the only root at 5, 5 level. I should be able to get either 4 alpha plus 2 beta or 3 alpha plus 3 beta, right? By shifting along either alpha or beta. These are the only two possibilities. All the others, we don't have to worry about them at all. There's no way you could get them. Out of these, 3 alpha plus 3 beta is what? Is it a possibility? 3 alpha plus 3 beta?
No, 3
No,
into alpha plus
it's a
beta.
multiple of a root, so it's out. So only possibility is 4 alpha plus 2 beta. Okay. Even if 2 alpha plus beta had been a root, and it is, right? 2 alpha plus beta is a root, so even this is not possible. Okay? Because it's twice a root. So 5, 6 level, no further roots. So this thing ends here. Is that clear to everybody? If you have a confusion, please let me know. This is a critical part of the argument. It's a pretty straightforward thing, but you have to be systematic. And it's very easy to lose out on a root like 3 alpha plus 2 beta if you're not being very careful. There is a way called using the Carta matrix, which we are going to discuss in the next class, which makes this more systematic or perhaps easier to follow. Definitely easier to automate on a computer. But this by itself is not very difficult to follow if you do it systematically. So is everybody clear about the full thing that we did now? Yes? No?
Yes, sir.
Nobody has any problems with this, right? Hopefully. So now, can anybody tell me how many generators does this G2 have?
10. Uh, 8. 8.
8?
And because
Why?
we have 2 from 5 on the simple roots, alpha plus beta from 5 2, 5 3, 2 alpha plus beta, 5 4 has 3 alpha plus beta, and 5 5 has 3 alpha plus 2 beta. So
So
in
how many?
total we have 1 2 3 4 5 6,
Yeah.
6 of the e alphas, and then we have a root simple root space and simple root
Okay,
space
just hold on.
consists.
Just hold on. Okay. Mm. So 6 and then
Okay, so 6, and then the rank is 2 because we have only 2 simple. So
yeah.
there will be 2 Karta subalgebra elements.
So how many is it? Everybody agrees that it's 8.
6 plus 2. Right.
The same size as SU3.
It
Doesn't that
should be
sound?
10.
Should be
It should be 10.
10.
Hmm.
No. Should be 14. 6 positive roots.
I'm sorry, 6, and there minus 6 from that side. So
6
12
positive roots,
plus
6
2.
negative roots, and the 2.
Yes.
I think you were using that kind of arguments to arrive at 10 somehow. I don't know how. But it's 14. So this is a much more complicated algebra than SU3, right? 14 generators, still rank 2, and all the roots, that is, all the roots are not just the ones we have found out. These and the negatives are all the roots. Clear? Okay. So at least one part of the story is done. We have found out all possible roots for a algebra. Now this procedure can be sort of, well, not simplified, but made a bit more algebraical by using something called the Carta matrix, which we are going to discuss in the next class. And that, so if you want to put this whole thing in a computer, that kind of the Carta matrix argument is easier to program than this one. But the basic idea is all laid out here. Okay, so I will have to wrap up quickly today because I have something else to do after this. But let me just briefly show you how the algebra can be, the other big claim that I made, that you can actually, given the simple roots, you can figure out the entire algebra. Okay. So next day my program is, we are going to do this for SU2, SU3, and for C2, or for G2. We'll have to find out all the entire algebra. At least we'll indicate how to do it. For the time being, let's go back to SU3 and try to get the basic idea about how to do this. Remember, there were two simple roots, alpha and beta, making an angle of 100 each, 1 unit long, and making an angle of 120 degree among each other. Now comes in our basic idea about whatever we know about SU2 and its algebra. That has already played a huge role in this, but that's going to play an even more important role. The SU2 representations are going to play a huge role in the rest of the argument. And that essentially means that whatever you learned about angular momentum, all these angular momentum eigenstates and so on, okay, remember we had this J3, Jm. Of course, we are using H cross equals 1 units, or these are actually the angular momentum by H cross. And J plus minus Jm, what were they? Anybody remember this? Come on, this is one of the most important equations you ever have.
It will be square root of j into j plus 1 minus m into m plus 1.
Well, that's for one of the signs. Or the other way of writing that would be minus plus m, j plus minus m plus 1. The one you were talking about was for j plus. This is for, I want both j plus and j minus in one, rolled in one. That's this equation. And there's an extra 1 by root 2 for our version of the SU2 generator, simply because remember our E plus E minus as a commutator of E3. So this relation is the same as the J3, J plus minus commutations that you had learned before. But if you just use Jx plus minus Ijy as J plus minus, there would be a 2 here. There's no 2 simply because you have rescaled E plus and E minus both by 1 by root 2. Okay, so in our version, that is the version we have been using so far, where there's no 2 in this commutation relation, the E plus E minus are really 1 by root 2 times the standard ones that we use in quantum mechanics courses. And so for us, okay, our E plus minus will essentially be J plus minus operators obeying things like this. Okay? Clear? Now the question is, remember, add E plus, add E3, and add E minus, they obey the same commutation relations, or at least they mimic the commutation relations of E plus E3 E minus themselves. That's of course why this is a representation. So basically add E plus, add E3, add E minus would also have the same kind of representations as SU2. So they will have states which can be characterized by JM values, and when E3 acts on that, you will get M out. When E plus acts on that, you're going to raise M by 1. When E minus acts on that, you're going to lower M by 1 with the same factors, because all these are simply a consequence of the algebra. Remember, they don't depend on what operators J3, J plus, J minus are. It just depends on the commutation relations, and that's it. Okay. So add E plus, add E3, add E minus will act on the eigenstates of E3. These, remember, are of course eigenstates of E3 by using these relations. So of course, now the question is, which E3 are we talking about? There are two possible E3s, right? Because there are two simple roots. Of course, there's an E3 corresponding to every root. So there are actually three E3s in SU3 because there are three positive roots. However, only the simple roots are things you need right now. So right now, let's focus on any one of them. Let's say A3 corresponding to alpha. So instead of trying to clutter up the notation by putting an alpha somewhere, I'm just going to write for the SU2 alpha and minus alpha, this pair. Okay. Then what is E alpha? Add E3 acting on E alpha. How much is that? Come on, this is the easy question. This is the easier part of the question. Quickly, tell me what this is. This is of course E3 alpha. How much is this?
E alpha plus E alpha.
How do you get that?
We use E3 equal to alpha dot H by mod alpha square.
Yeah. So here is alpha dot alpha by mod alpha square comes out, right?
Yes.
So E alpha definitely forms, well, the question is, this corresponds to M equal to 1 in the SU2, right? Eigenvalue M of 1. But what is the value of J? For this? That is, how many times can you raise it or lower it? By the way, this is a trivial question which shouldn't even be asked. You should be able to tell me without even, well, okay, you shouldn't be able to tell me without me asking it because you would not know what I would be asking. But you should definitely be able to tell me the answer immediately.
J equal to 1 because E2 alpha cannot be there. Like if you had add E alpha acting on E alpha to raise it, so that won't happen because it's 2 into alpha. It's a multiple.
Yeah.
So J should be equal to 1.
Okay. So what you have is J is 1. So this is basically a spin 1 situation. This is one element of the spin 1, and this is the highest weight state actually. The other states are trivial. So here, okay, remember that when we say state, we mean elements of the vector space. In the adjoint representation, the elements of the vector space are the operators, are the Lie algebra generators themselves. So this is the highest weight state of the J equal to 1 representation, Which are the other ones? I will let you figure that out. So which are the ones? Of course, if spin is 1, there should be a spin 0 and spin -1 element. Those are trivial. So I will just ask you to figure them out yourself. Which ones are the spin 0, spin -1 for this? But let's quickly look at this other thing. What about E beta? What is this?
Alpha dot beta by mod alpha square.
Yeah, how much is that? Times E beta, of course.
Thank you.
How much is that?
Minus half. Yeah.
Yeah, and this actually corresponds to P equals 1, Q equals 0, remember? And what does that tell you about J? How much is J then?
We can raise beta in the direction of alpha once and we cannot lower it.
Yeah, so what is J? So how many states in the multiplet? In this whole process of this invariant space which you get by action of this E3, E plus, E minus on E beta. E beta alone is not there. You can shift it by applying E plus, right? But how many states span that space? What I'm asking is, if you ask yourself these questions, how much is add E plus E beta? How much is add E minus E beta? One of them is trivial, this is 0. This is going to be a possible state because there is an E alpha plus beta, right?
Yes.
So how many states are, and then if you now look at E alpha plus beta and apply E3 on that, you're going to get E alpha plus beta back with a factor. If you apply E plus on that, when I say E plus, I mean add E plus, you're going to get 0 because you can't shift in again. If you apply E minus on that, you're going to get back E beta, right? So E beta and E alpha plus beta together form a vector space which gives me a representation of on which add E3, add E plus, and add E minus will act, and you get an invariant space. You're not going out of that space. Is it okay?
Okay.
And what does that tell you about the dimensionality of the space?
It's spanned by E beta and E alpha plus beta, so it's two-dimensional.
And what is the value of J then? Remember, this is SU2 we are talking about. We are talking about two-dimensional invariant subspace of SU2. Which value of J?
So it will be half and minus half.
Yeah, and sort of that was obvious, right? This is minus half, this is the M value. And you can't lower it further. So this is the lowest base state of that representation. So M is minus half for that. The lowest weight, J has to be half. Okay. Now, why is that useful for us? Because this immediately is telling me what this is going to be, this commutation relation, right? But in addition, how much is this going to be? We know this has to be E alpha plus beta times some factor. How do you figure out what that factor is? What is going to sit here? How do you figure that out? Come on, E alpha is what? Basically E plus that we were talking about is E alpha divided by the length of alpha, which is in this case 1. So E plus, add E plus E beta is nothing but E alpha comma E beta. What is that going to be? That's going to be the next step state in the representation, the next higher state in the representation with a factor. Where will the factor come from? Forget everything else. This is SU2. E beta is the lowest weight state. That is, E beta basically is the state half minus half. When E plus acts on that, what do you get?
Square root j plus or minus 1, that factor.
Yeah, and what is that factor? You should have at least this committed to memory. For spin half, what the factors are. That is S plus acting on half on the down state. How much is that? That's the standard for spin half formalism that we use. How much is S plus acting on the down state? It of course is the up state with a factor of how much?
Root 2, I think.
Well, actually 1 in the standard textbook sense, but here it will be 1 by root 2. The 1 by root 2 simply comes from this additional factor that we have. Okay? So basically, some of the commutatives you can figure out simply from the SU2 algebra itself. The other commutators, we are going to do that next day. I just have to run off to another meeting now. We will do the other commutators using basically the SU2 algebra and just nothing more than the Jacobi identity. And next day we'll start by first showing you how to write down the entire SU3 algebra with starting from these considerations. And then we will tackle the more complicated one there, G2, which will turn out to be, okay, I will not write down all the commutation relations of G2 because that's going to be a long thing. But the basic idea is pretty straightforward. And then we will discuss this Karta matrix approach, which sort of makes writing the thing down a bit faster or at least more systematic. Okay. I've got to rush off today, so I can't really take any more questions. Let's just stop the recording.